ratio. But you can do more.
Okay.
And please go ahead when you're ready.
Thank you. Okay, let me thank the organizers first for this invitation. And my talk is accessing the origin of the nucleon mass. It will be a very biased presentation. Let me start with something really trivial just to get going. And this question we would like to answer is, what is the origin of the hadron masses? Computers gave an answer to that question. Okay? Everybody knows, it seems, that the mass of the hadrons, they come from the gluons and nearly massless quarks. And where is this confidence coming from? This slide was already shown this morning, or this afternoon, or this night, I don't know how perspective. And well, it was published in Science, it got to be right? That this is the ab initio determination of the light hadron masses. Okay, there are some input, of course, because you have parameters in the Lagrangian, and you can see that QCD actually reproduces and is able to make predictions for the hadron masses. So why we are not satisfied yet? Essentially, we want to know, as Wilczek said, is how did it happen? So what is the meaning of this question? The meaning is that we want to make models and we want to mess around with parameters of our models such that we can understand what is happening with these quarks and gluons, such that they reproduce the masses of the hadrons, and also the Goldstone boson nature, or pseudo Goldstone boson natures of the pion kaon. Okay. So this is, in my view, the main driving force, driving paradigm for us to keep asking this question. Okay. So let me, this is also very trivial and very well known, but perhaps some students or people that don't work in this, it's just a small reminder. It goes back to more than 40 years. Okay, suppose we have a hadron mass, a hadron state. Okay, and then this is the energy momentum tensor, so the expectation value from Lorentz invariance. So we get this general expression. So, and if we take the trace here of this energy momentum tensor, we get then essentially the hadron mass. Okay, so let's look at this limit here, this theoretical limit that the light quark masses are 0 and the heavy quark masses are infinite. So they essentially decouple from the theory, and since we don't have any mass scale in the Lagrangian, so the action is the scale invariant. And once you have an invariance, you have a conserved current. And in this case is the dilatation current, which is given by the essentially the energy momentum tensor. But since this is a conserved quantity, okay, and this is conserved, I get that the trace of the energy momentum tensor gives 0. So the hadron masses must be 0. So what is wrong with this argument? We know the proton is not massless. Okay? It's simply because all this analysis that was done here on this slide, okay, was on the classical level. Okay, the quantum action, the quantum Lagrangian Okay, when whatever calculation you want to do, you have to regularize it because of the ultraviolet divergences. Okay, once you introduce a regularizer, doesn't matter dimensional regularization, cutoff, whatever. Okay, you have to introduce a scale, a mass scale. Once you have this scale in your theory, so you don't have any more scale invariance. Okay, then you can show that the trace of the energy momentum tensor is not zero anymore. It's given by this combination here of these gluon fields. Okay, and this is what is known the trace anomaly. Okay, so the hadron mass will then come, if I repeat the calculation that I did in the previous slide, I get that the hadron mass comes entirely from this gluonic operator. It doesn't mean that quarks don't contribute to here, because you still have quarks in your theory and they will contribute. Okay, some people try to separate the contributions from kinetic energy and quarks and gluons. Okay, but there are issues there that I don't want to enter regarding frame dependence and other issues. Okay, now if for real QCD or real world, the light quark masses are not zero. The heavy quarks are not infinite mass. And so the hadron masses actually get an extra contribution that you might call it a Higgs, an explicit dependence on the light quark masses, which is of the order of 80 MeV if you say integrate out the heavy quarks. Okay, so you still have a substantial contribution from this operator here. Okay, so then we like to say that the hadron masses come essentially from gluons, okay, meaning that it comes from this operator. Okay. So how can we access this matrix element? So this is the biased part of my talk, that we can access this matrix element through heavy quarkonium nucleon scattering. Okay, so a heavy quarkonium is what is, say, the eta C, the J psi, the upsilon, eta B, and so on. Okay, so why is that? This is because this heavy quarkonium, they are small objects, okay, and they interact with the nucleon by exchanging gluons with the nucleon's light quarks. Okay, why? Because they don't share the same quark content. Okay, the heavy quarks, they don't have the heavy quarkonia, they don't have light quarks, valence light quarks. Okay. So low relative momentum, the gluon wavelength is of the order of the nucleon radius, and since the size of the heavy quarkonium is less, depending what heavy quarkonium you are talking about, this heavy quarkonium is much smaller than the nucleon radius. So then you have the picture that the quarkonium behaves like a small dipole moving in soft gluonic fields. Okay, it doesn't mean two gluons they are interacting. These are soft gluons. Okay? And if this picture is valid, you can use what is called the multiple expansion in QCD, similar to the electrodynamics, electromagnetism, multiple expansion. You can express it in the language of the OPE, the operator product expansion. So why is that helpful? It's helpful because the scattering amplitude of the quarkonium on the nucleon in the forward direction. I'm writing it here for the forward direction, can be factorized into the matrix element we want, and here a property of the quarkonium, which is the quarkonium polarizability. Okay, this is a huge assumption, okay, that is valid for heavy, say, sufficiently heavy quarkonia, okay, and once you know this property of the quarkonium, then you might have access to this matrix element that has to do with that gluons. It's not exactly this matrix element that we have here, okay, but I will show the argument for saying that this is essentially, that matrix element is essentially given by this one, okay? So this is the argument that this inequality here, what inequality I'm talking about, this is G min E. G min E is the matrix element I want, okay? But this is essentially given by this because this is heavily suppressed in a nucleon, okay? So we essentially having this, okay, we have this. So how to access this experimentally, how to access experimentally this matrix element. Okay, here I will focus on J psi. Okay, from the outset here I'm already with problems with J psi because it's not so, perhaps the multiple expansion is not valid, or it has some limitations. You have to go to higher orders or something like that. But that's just for the sake of argument, stay with that. But this, all what I'm saying here will be valid for the upsilon as well. So then we have to wait for the EIC, okay, or go to heavy ions, as I will argue in a few slides. So what do we know about the J psi nucleon interaction? We know a little bit. Lattice simulations are not, say, the most precise lattice calculations, but they essentially, and together with models too, okay, that this interaction is weakly attractive and is S-wave dominated, okay. And if this is weakly S-wave dominated, I will be very happy if I will know this number. This is the scattering length of the quarkonium nucleon scattering. So we need first to learn a little bit about this scattering amplitude. Okay. So this is actually experiment that we already have results. Is, say, this GluX experiment, and people have analyzed the data. Here are two references, okay, and it came out something kind of surprising regarding previous estimates for this scattering length. It's rather small, 100 times smaller than some earlier theoretical estimates, okay? There are some issues that some were already mentioned in the previous talk by Rolf, that, okay, this was not mentioned, but this is one of the most, I think Craig asked this question, is this, that you actually don't have access to the forward angles with electron scattering here, because the minimal T at forward T is 0. Okay? So it's of the order of the modulus of T, right? Is of the order of 1 point GV. Okay. squared. So we have to make extrapolations. Okay, different sorts of extrapolations lead to different answers, and some use dispersion relations to relate the imaginary part with the to get the real part from the imaginary part. And the other issue here is vector meson dominance, that for J psi might be problematic because the size of J psi is not so small. And there's another issue that it perhaps J psi has not been fully formed here in this process of this gamma transforming into J psi. There is not enough time for this to be completely formed. So the rescattering that is happening here on the nucleon is a CC bar, but is not yet, say, a J psi. Okay. I have not made any calculation that I'm just reproducing here things I read about this possible explanation for this very small number. Okay. Actually, I collected a table here from this latest publication, I think came out a few weeks ago. And here they collect all, okay, this is the analysis, their analysis. That is 10 minus 3 Fermis here, 3 times minus 3, 10 times 10 to minus 3 Fermis, 3.08 and so on, these numbers, but compare the numbers here that we were playing a few years ago, okay? It's 100 times larger than these numbers here, okay? Is this then a signal, or is this telling us that it is hopeless to get any information on the gluon distribution or scattering lengths or things like that? This I'm not Demon's lawyer, okay? I will not defend his calculation, but it looks very interesting from exactly the same data from this GluX collaboration. Okay, this forward, this is scattering amplitude is not quite forward, okay, but this expression here is valid close to the production threshold, which is not so small, okay. And if you fit this data to this form factor, such as this form factor, you can extract the radius of the mass distribution in the proton. And you see it's of the order of 0.5, okay, which is kind of half of the charge radius of the proton, okay. So you see the data, okay, and although the scattering length is very small, you still can make some predictions regarding, this is much richer than just the scattering length, okay, because this is not forward, this is a bit of forward, such that you can have make the derivative here, but then you have to extrapolate, and all these issues appear here again, okay. Fine. Another possibility that I'm advertising, but I have not done calculation yet, okay, is this antiproton annihilation on the deuteron. And my last talk for Amber on a workshop we had, I had pi0 here, and then I got a lot of complaints about experimentalists saying, look, pi0 is very hard to detect. That's fine. Then we can look at charged final states, which is much easier. And this then requires a calculation. There are calculations available for pi0 production. I have not seen for pi minus. I have to do it by myself. I have not done anything on that, but this is a possibility too, okay, to access this. Again, here we have kinematical constraints, of course, that this will not be actually quite forward. And this has to be done. It's very similar to a previous prediction we have done some years ago for D mesons scattering on the proton is essentially the same thing, but here we know a bit more. The antiproton-proton annihilation producing D mesons, and this is we made the prediction for Panda, but nothing for BITS for eventually for Ember2. Okay. And another possibility to have access to that matrix element, okay, that doesn't suffer from this problem of not accessing forward directions, and there's no problem with threshold behavior here. Of course, there are many other issues regarding this femtoscopy. How much time I still have?
I think you can take 5 minutes or so.
5, okay. So what is this about? Okay, you produce here in a heavy ion collision a lot of particles, including, of course, J psi and nucleons, protons and neutrons. And as a final state interaction, then you measure the correlation between J psi or epsilon with the proton. Okay. And what is the observable is a ratio, okay, of you measure J psi and a nucleon from the same event, and you divide by the same correlation, okay, same the particles that you detected at some pair of momenta, and from different events. This is kind of the background, okay. And so if this is different from one, this is signal of a correlation between the J psi or epsilon and the nucleon, okay. Then, of course, life is not so easy. You have many experimental issues here. You have, say, you can induce correlations here that has nothing to do with these interactions between J psi and nucleon. You have problems with momentum resolution and many other issues. But this essentially, how do we get from the experimental measure? You can make a link to the scattering wave function of the system of the J psi and the nucleon. Okay, and this is the source. It's the size from which the proton and the J psi are emitted. Is not the size of the fireball. It's not the size of the entire fire, but from the emission region, which is smaller, much smaller than the size of the fireball. Okay, so this is the linkage. You have here the experimental measurement, and here is your theoretical model. And here, of course, is also an issue. What source are you using? Okay, what source you are going to use? But this is just say that it's not complete fantasy. People have already extracted. Say this was last year. Say the low energy kaon proton scattering. Okay, we had a prediction many years ago, which is this red curve here, and you see that Alice actually validated our model we had for the kaon proton scattering. Okay, and Alice, for example, has many other femtoscopy studies of lambda n. So then we made a prediction for lambda cn, which is very important for charm hypernuclei. And for the J psi nucleon, I use models, okay, available from Lattice, from other models, just to get an idea what can we expect from such a measurement. Okay, so this is all then, since my time is running out, this is very standard, okay, then that you can, in some approximation, call the Lipnitsky-Leibovitz model, you can relate this correlation function directly to the scattering amplitude. Okay. This formula, of course, has limitations, but for the kaon and the lambda, this works very nice. For J psi, not so clear. Okay, and essentially, for very low relative momentum, then I can relate the measurement of this correlation function to this matrix element that I want. Of course, I can also have access to the cross section, okay, and also have access to that form factor that Dima has calculated, okay. And these are the predictions. So these are for different values of the scattering length, and you get the scattering length. If the scattering length is very small, like the one that was extracted from the blue X experiment, we are down here. So the correlation, you have to blow up this region here, and then you get into the experimental issues of momentum resolution in many others. Okay, so life might not be easy if this scattering length is really very small. Okay, but here I don't have to spend money to make the experiment. Actually, the data are already available. Okay, what you need to do is just to take this data that probably is on computers, okay, pay a student or a postdoc to make this data analysis. You don't need a new experiment. Data is already there. So I have to convince the experimentalists of Alice, at least, okay, that this is something that might be interesting to look at. Modulo all these complications, the experimental complications that might have to regarding J psi. But people tell me J psi is very easy to detect, but then you have other issues that I'm not a specialist, and it's easy for me to make a calculation and let the experimentalists tell that it's nonsense. So far, I have not heard anything bad yet. Okay, so my summary is that something that everybody knows, that is the Hadron mass comes from the trace anomaly. And I commented upon this electron in photoproduction and commented some issues due to extrapolation, vector meson dominance, formation time, and all that. And then I suggest a calculation of this for Amber and Panda, and also femtoscopy in high energy proton-proton and heavy ion collisions. So how about the pion? It's the same, but if the J psi proton scattering length is small, J psi, there are some there are lattice data for J psi pion, but the error bars are very big. Okay, so there is a very recent one for Upsilon pi. I'm looking into that and see if femtoscopy of J psi pion will be feasible. Okay, of course I left out many things, the validity of the multiple expansion, factorization in this process here is a big issue. This electroproduction, right? We are factorizing this vertex of the electromagnetic part to this rescattering from that. Okay, this seems not to be a very it's not settled if the factorization is valid for this process. And so there are many issues that we have to look at. Thank you.
Great, thank you very much, Gastao. Let's see, so I think, yeah, any questions specifically to Gastao at this point? There's a question, and John, I think, was first in my list.
Thank you. This is a very interesting proposal of doing femtoscopy with J psi. I'm actually from the Alice experiment by chance. And yes, I confirm that, of course, we can do this. We do femtoscopy on a daily, it's a bread and butter for us. I think, however, for the heavy ion, I see a conceptual problem because in heavy ions, our system expands. So you have, it's a tricky thing. It's a, you have correlations coming from the collective expansion of the system, and those are characterized by radii of about 6 Fermi or so.
Okay, you are talking about the size of the source from the emission
Exactly,
source.
of the homogeneity.
Okay.
Source, yes.
Yeah, and I need small sources to get a bigger
Right, exactly. That's why
right.
proton-proton
Yeah.
is, I think, the system to look
yeah,
at.
I propose proton-proton and mention heavy ions because
Yeah, in heavy ions, there is an additional problem where because the background is very large. So there for the J-psi identification. So I think that will not be practical, so to say. But in proton-proton collisions, I think our current, at least in ALICE, our current limit is statistics. We don't have enough. Well, we have a bunch of thousands, right, of J-psis.
J-psis, okay.
Yes. Well, more is available via the LHCb experiment that just has more luminosity. So I think maybe a combined effort would be an interesting thing to
okay. I will send our paper to you then, perhaps.
Thank you. This is a very, very good idea. We will have to pursue it somehow. The question is when the results could come. It will take some time.
Okay, thank you.
Very good, thank you. Christian is next.
Hello, Gastao. Very nice talk.
Hi, Christian.
Can you go back to the slide where you show the blob with the J-psi production?
The electroproduction, right?
Yes. Okay, so I guess very naively, this process could happen by 2 microscopic processes, right? Either the photon couples to a quark in the proton, and then there's some radiation of gluons which produce the J-psi, right? Or the photon could couple to the J-psi after it has been produced by gluons radiating from the proton. Is there some insight from
now, the present the way people analyze this is through vector mesodominance. You have the gamma here, the virtual gammas, transforming in J-psi, and then you have the rescattering. And then you use these factorization formulas just to factorize this. I don't have the expression. The next talk I will have this expression. You actually rely on J-psi being reduced here through vector mesodominance.
That's a third process, actually. Is there some idea from model calculation which of these microscopic formation mechanisms is dominant? You're saying vector mesodominance obviously has been considered. Have the others been considered?
I think there are some calculations there, but it's not the way people analyze this data. No? Okay. This is a Phillips formula that is known as Phillips and Barger and Phillips, where you see nicely there the factorization between this vertex and then the J-psi rescattering on the nucleon.
Okay, thanks.
Okay, the German next, please.
Yes, Gastao, very nice talk. And this is extremely puzzling, this so small scattering length, 100 times what was estimated. But there is another puzzle, is that some of these ideas came from this 1988 paper where the Krein anomaly in elastic proton-proton scattering was attributed precisely to the charm threshold. So if this value, if this very small value came to really to be confirmed and not a bias of analysis or whatever, then this interpretation of the Krein anomaly has to be explained by the other mechanism. And there are not that many mechanisms in QCD to explain the Krein anomaly. I recall it was parallel
Right.
spin proton versus anti-parallel. So this is another challenge
Right.
that such a small scattering length brings.
Okay. I will bet money on this formation time. I might be wrong, but this formation time, that what is actually rescattering on the nucleon is not a fully formed shape psi.
This has really to be re-examined very carefully because it brings some fundamental questions.
Right.
Thank you.
Thank you. Reinhard, next. Please go
So
ahead.
thank you for this very nice talk, Gastao.
Hi, Reinhard.
Before I put my first question, I would like to make a comment to the heavy ion collisions. Yes, it's true. In heavy ion collisions, you have this expanding system. However, the shape psi will be formed quite early, and the shape psi will leave the fireball quite undistorted. So I think ELIS is a wonderful opportunity to study that.
Reinhard, the problem is the source here. I'm sorry.
Yeah, but the other thing is, again, this astonishingly small scattering length. And we know from other parts in physics that if you have such kind of small scattering length, quite often you have phase-shifted competing microscopic mechanisms. And this relates to Christian's question, because you said one way of thinking about it in the sense of vector meson dominance, that the off-shell photon mixes with the shape psi, with the vector meson, but practically a QED effect and suppressed by the QED coupling constant, whereas forming, as the photon hits a quark, radiates gluons, and the gluons form the shape psi as a strong interaction process. Now, of course, we know that if it comes to the low energy reason, for the light quarks, the rho zero as applying the vector meson dominance in the sense that the off-shell photon mixes with the rho zero is very successful. However, if you have much more energy available, you would expect the gluon-mediated mechanism to compete. And if you have now two mechanisms which are not coherent, but maybe with a shifted phase, this might easily explain the low scattering length. Don't you think so?
Yeah, it might be.
Yeah.
I'm not involved in this, and also this factorization, because this thing you are bringing in, these gluons, also brings problems with factorization. Right?
Yeah, that comes in addition.
Yeah. Now, regarding here, this source size of a heavy ion collision is much larger than the emission source.
Yeah.
And then, if you look here at the signals, they drop violently with the size of the source. You see, this is a source of 3 Fermis regarding to 1 Fermi. Okay, you see, it drops from 2 to 1.3 and so on. And if you put 6 here, okay, then it actually drops down here and you lose the signal. That was the remark of Professor Andronic on the heavy ion drawback in femtoscopy.
Okay, thanks.
Okay, I think, Anton, was this a direct comment to this one?
Right, if I may, thank you. To the comment that the J psi is formed earlier. Yes, in principle, it would be on the argument of times of 1 over mass. But at the LHC, we have ample evidence that the charm quarks are deconfined and the J psis are at least in majority formed very close to the phase boundary of the QCD. So this is something we see in the data. So yeah.
Yeah, however, if you follow this picture, I remember talks of Peter Braun-Munzinger arguing this way by looking for the scaling of the different cross sections with the mass. That he was arguing that this process is dominated by the charm quark mass and that it's formed at the phase boundary. But would it then not be especially interesting to confirm, as to falsify or verify further such a picture?
Yes, I think it would be, absolutely. Yeah, part of it, so to say. It's a tough thing at the end, right? Because of the convolution of the source, so our rather large background in lead-lead collisions. But yes, we have to keep it in mind. Yes, I agree.
Yeah. Of course, I have some problems to understanding what precisely a deconfined colored source should mean in the context of a gauge theory, but okay.
Okay, thank you. Franco, please.
Yeah, thank you. And Gastao, thanks for the nice talk. Actually, I just want to continue with Christian's question because he was mentioning two possibilities and asking whether there are calculations comparing different mechanisms. There is one more possibility or one more mechanism. That's the photon couples to open charm pair of
Right.
DD bar or lambda C bar.
Yeah. Okay, but this seems very say suppressed, right, compared to this leading order.
Not really, because actually in your slides
you mean
table,
lambda C, right? Lambda C.
Yeah, lambda C D bar threshold. Actually, yes,
right.
lambda C D bar threshold.
Yeah.
The threshold is just 100 MeV above deep side proton threshold. Okay, this is very close. And in your slides in the table that you got from Igor Strakovsky's paper, one of them, one of the result actually is taken from our paper on couple channel calculation. So we did some calculation by coupling the photon to DD bar and to lambda C bar, considering lambda C D bar couple channel, and without any vector meson dominance, by only considering this couple channel mechanism and using model values for the involved couplings, and taking.
So which one is this one? Which one is it?
Can you share your slides? I cannot remember.
It's not shared.
Yeah, I think it was stopped.
You see it?
It's a start. Yes, thank you. Thank you. So in the line photo production via open charm channel 2020 is this one. Go up.
The
go
first,
up.
the
Yeah,
first
this one. Yes. So here we can
it's
see
also very small, right? It's also
that's
very
right.
small.
That's right. That's actually by this couple channel mechanism using.
I know this
the
paper.
Euro,
I know.
Yeah. Euro values, and then actually this gives cross section of the order of the GluX merit data.
Okay.
Thanks. This is a comment.
Thank you.
Yeah. Thank you.
All right, thank you. Let's see, Craig, did you want to come back to your point from earlier here at this point?
I think the issue has been quite well covered, that vector meson dominance is unlikely to be a useful tool in analyzing this process. And so you have to start looking for other mechanisms, and the other mechanisms are quite complicated. And no one has properly analyzed those, not for many years. There have been some model calculations, but they were done 20 years ago and they haven't been revisited. So the whole connection between this Jape psi and the trace anomaly on the proton is very, very rather shaky.
Right, yeah, thank you.
Yeah, but I think this remark regards this photo production, right?
Yes, the remark certainly regards the photo production.
Yeah. Right.
All right. Let's see, Feng, there's another comment you have, or your hand is still up?
Sorry, I forgot to lower my hand.
Okay, great. Thank you. Let's see, any other specific question for Gastao at this point?
I think we are in the discussion.
I think we have a little bit discussion. I think we're already in the discussion basically, so, which is fine. Yes, we have about maybe 10 minutes of the time for the discussion about basically the first these two talks in the session. So basically about the hadron mass and opportunities, in particular here at ERC. I think we have other discussions later in this week. So I think we can spent a few minutes. I think from what we saw in the previous two talks here is essentially we are of course on the quest for understanding the mass essentially of proton, pion, kaon, hadron in particular or in general. There's different discussions about the decomposition, different ways of perhaps measuring. And if we look at, I guess I could share very briefly, in case that there's any questions. I mean, this is essentially from the slides that we just looked at. So, okay, mass of proton, pion, kaon, obviously it's very important. We have to understand it. We have looked also, we have seen in the previous talk, the mass budgets, essentially saying that that there are different contributions. And again, we have to understand how to measure these. In particular here, again, you see proton, kaon, and pion mass budgets. Again, I mean, the main point here being they look very different. And of course, we heard about much more detail earlier about it. And then also we have seen that there's different parts of the whole have to contribute here. So there's the experiment, there's the lattice. We've heard many things about the continuum calculations and so on and so on. Importantly, as inputs, the global analysis, 3D images, and then of course understanding QCD. And then we've heard in the very first talk in this session about the role of ERC, where potential measurements can be made. Okay, we have been discussing much about JSI now. We also heard about the pion form factor, possibly contribution of measuring the kaon form factor, and then various structure function measurements and how the ERC might impact the picture. Now, maybe the question, just to say we have not many minutes left, that's why I'm keeping this short here, is so where are we with actually getting to these points in terms of all the different contributions? I think experimentally we have clearly heard it. We have heard something about the JSI, that there's certainly some work to be done. Are there any other points maybe that we should think about that we're missing to basically take advantage and benefit from these from this particular facility now, the ERC, bringing data in the next decade or so, to actually make good use of those? So that's maybe the question I want to pose here. Okay, now to, I think, stop sharing because I cannot see if anybody is raising their hand. I think various people are unmuted. I don't know if that means you want to comment.
Can you perhaps repeat your question? I didn't quite get it.
Sorry, my question was, I mean, we have the facility coming up, the ERC in particular, and we hear about other facilities later on. And my question is if we need to think about on the theory side or phenomenological side, if there's anything we need to think about to get ready for actually make good use of the data that are expected to come in the next decade or two or so.
I think the answer is yes. We have a lot of work to do. There is so much. One thing that comes to mind always is this PDF fitting.
Yeah.
There is so much more that has to be done there. Rolf emphasized our need to understand the gluon content of the pion and the kaon, and the sort of bizarre twist that some people would like to argue that there is no glue in the pion at all. To get answers to these questions, we really have to have very reliable tools for analyzing the data, because we need to extract PDFs to answer these things. And if people are not going to go to next to leading order and next to leading logarithm, we're still going to be in the same position 20 years from now. So there's a lot of work that has to be done on the phenomenological side. Then we have the theory. We have continuum and lattice working very hard to try and produce the answers we need. But effort there has to be expended. Again, many simplifications are made, and we have to eliminate those things until we all agree on the outcomes. So I think the meetings like this, the questions that are being raised, hopefully make people think about what they have done in the past and what they can do in the future to overcome the limitations of the previous work and drive us forward. We have, what, 10 years for the EIC, 10 years for AMBER. JLab is taking data now. They'll be analyzed. We don't have as much time there. And EIC in China, well, can't be sure when that might happen, but the clock is ticking. A lot to be done.
Right. So are you saying essentially these efforts are ongoing, or is it something we should be worried about where efforts have to be started?
I think the efforts are beginning. The conversations we've had over the past 18 months, 24 months, have raised awareness of the problems. But you know as well as I do, we still have this chronic problem with the pion's distribution function. The arguments that still continue over whether it's greater than 2, somewhere near 1. And there are many reasons why this should have been solved already. But the doubt, the fog is still there. And it needs a lot of work to clarify this. It's not until that's, in a sense, if we don't clarify that, then no amount of new data can take us forward. We have to reach the point that, one, we all agree on what the large X behavior should be, which is actually, that must be greater than 2 at any measurable value of experimentally measurable value. And then we have to develop the theoretical analysis tools to take the data to such an answer. And until we can agree on that, then all new data is almost wasted. That's an extreme statement, and I don't really mean it, but we have to keep that in mind. Data is not alone going to provide us with an understanding. As we've advertised in many places, theory, phenomenology, and experiment have to really come together to solve these problems. None of us alone can do it. At least that's my view.
Yeah, I think that brought it to the point, Craig. Thank you. All right. I think that's even a very good closing note for the first day. But let's see if anybody else has any comments on this. Patrick, please.
Hi, yeah, so since we're talking a little bit about Pion PDFs, I thought I may give a little bit of input. I think, Craig, you raise a good point that we need a lot of theoretical input in the phenomenology. We need all these communities to kind of come together, phenomenology, theory, and experiment. The problem with the Pions right now is that there's such little amount of data that's usable. And if we want to try to have as much unbiased phenomenology fit, we're at the mercy of the data. And we can put in theory as much as we can, but still we have to look to what the data is telling us. And so that is, I think, the current status, that we need to really try to be as unbiased as possible and look to the data to tell us what the answer is. And unbiased phenomenology fit, we're at the mercy of the data. And we can put in theory as much as we can, but still we have to look to what the data is telling us. And so that is, I think, the current status, that we need to really try to be as unbiased as possible and look to the data to tell us what the answer is.
I think that's true. The data is important, of course. My point is that we have to put the best theory together we can. To the present day, I judge that too many poor truncations have been made, and so they obscure what the data is actually trying to tell us. And I think we need to eliminate those truncations so that we can really get to what the data is pointing to.
I see.
I think,
That's a good point.
you know what I mean.
Right. Very good. Yeah, any other comment on this, to this topic? All right. I think then we're just on time to close this session.